something smaller. So let's say, let's say Q is less than little p. Well, if P is in alpha plus beta, would you agree that little p is the sum of two things, R plus S, where R is in alpha and S is in beta? Agree with that? Okay, this is in your book, so you don't need to write it down, but if it helps, just follow. Would you agree so I'm now looking at Q and I want to know, is Q also an alpha plus beta? Well, what does it mean to show that Q is an alpha plus beta? I need to write Q as the sum of two things, something in alpha and something in beta. I know P is the sum of two things, R and S. Okay. Well, would you agree? So notice, oh, this is a neat observation. If I take Q minus R, would you agree that because Q is less than R plus S, Q minus R is less than S? Oh, but Q minus R is less than S. What does that mean? Actually, I have it written in my notes backwards. So let me do this. Q minus S is less than R, just to agree with my notes. Well, what does this mean? Q minus S is less than R, but R is an alpha. So where is Q minus S also in? Because alpha is closed downward. It's also an alpha. So Q minus S is an alpha. Then, so this is the beauty. Here we go. Q is, isn't it really just Q minus S plus S? Where Q minus S is in alpha and S is in beta, right? As desired. This is a good way to end a, when you end with the words as desired, you're reminding the reader that you've shown something you were asked to show. Okay, and you say, reader, you go back and remember what it was you're asked to show. Okay, all the proofs they look like this, okay? They're cut from the same cloth. Okay, they all look like this. I'm not going to do the other one. So here we go. Close downward, and what was the other one? No largest member. Check. It's a cut. Great. Okay, so we have an order. We have an addition. We would want to show the properties, show the axioms for addition. Show the axioms, A1 through A5. And again, I'm not going to do all of these. I'm just going to have you think through why they should be reasonable, and you can check them in the privacy of your own home. So for instance, commutativity. If I define beta plus alpha to be all S plus R, such that blah, 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 is it clear that alpha plus beta is going to be the same collection as beta plus alpha? Why? Addition itself is commutative for rationals. So commutativity for reals follows from that for rationals. Nice. Okay. Associated property, same idea. So that's A2 through A5. Is it clear that the first one is that it is a cut? So we've just done A1, right? So that's A2 and A3 are the commutative associative properties. Additive identity and multiplicative inverses. Oh, so we should at least say what those are. So what's the additive identity? Let's give it a name. We'll call it, oh, I don't know, how about 0? We'll just put a little star there to remind ourselves it's not the number rational 0, it's a collection. What should play the role of 0 in tonight's play? Good, the set of all negative rationals, Q minus. Oh, okay, that's cool. So you should check that alpha plus 0 star equals alpha as cuts. But what does this mean? these cuts are sets of rationals, collections of rationals. So really what this means is, so verify, well, how do you verify two sets are equal? You could show that one contains the other. You verify that alpha plus 0 star is in alpha, and alpha is in alpha plus 0 star. Okay? Let's talk through that as well, and you'll see in your book why it's true. If I take something in this collection alpha, and I add something from 0 star, which are what? Negative rationals. Is it clear that it's still in alpha? Yeah, because you add anything negative to a number here, it only gets smaller. Why is that still in alpha? It's closed downwards. Beautiful. With me? Okay. Let's go the other direction. Why is it that if I pick something in alpha, in this collection, it's the sum of something in alpha plus something negative? Member. Okay, good. So what you're saying is, because there's no largest member, you can write alpha. So here's the thing that's in alpha. That's in alpha. Here's P. Because there's no largest member, take something, let's call it Q, and we'll write P as Q plus the Q minus P. P is Q plus Q minus P. That's the basic idea, right? And this is the thing that's in 0 star. Now you have to be a little careful here. So you have to check this, right? But this is the way to go. This is a proof sketch, literally a sketch. Okay. Now what we don't want to encourage you to do though is practice writing this argument out and then check and see if the book does it the way you did it. Okay. Excellent. Other thing we should probably say is, what is an inverse? The additive inverse. This is a little more complicated. It's not obvious what this should be. So if you want to talk about the inverse for alpha, so here's the picture. Here's alpha. It's all these points here. Now, how would you find its inverse? What would play the role of minus alpha? So let's say here's 0. What would play the role of minus alpha? Well, there's part of you that kind of wants to just invert this thing, right? But then you get something that goes off to the other side, right? So you have to be a little more careful. So I'm just going to say, and then I'm going to throw up a definition that's going to look unmotivated. But it's motivated if you think about it. It's going to consist of all rationals such that there is a number, r, bigger than 0, such that minus p minus a little bit is no longer in alpha. And your job then is to show alpha plus beta is 0 star. Okay, so we're looking at all collections of rationals. So in this picture, beta, oh no, I just lost my chalk. Okay. It fell in the recesses down here. We're just going to look at all the rationals which have the property that when you look at anything, if you look at minus p, you can subtract a little bit and it's not in alpha. Okay, so let me give an example.